Hello, gals and guys, and happy Friday Eve, everyone. Now, I know you guys have been working super duper hard over the past several weeks, and I'm so confident that if you just keep at it just for the next several days until your exam next Tuesday, that you're going to disintegrate your AP exam come next Tuesday. And I'm so confident that you're going to do well on your exam that I believe your grade is going to be this score right here. So keep at it. You just got a few more days left, and it'll all be over before you know it. So before I get into some review material for today, I wanted to talk about an update that the College Board has done with their platform that you'll use to upload your work. And you can see this in the AP demo site, and you can practice this if you want to go and use a different route than what I've already talked about. I'm assuming that all you're going to write out your responses first on paper and then ultimately take pictures of your work to upload that to the College Board site. And if you do take photos, you have to take a separate photo for each page of your work, making sure that each photo has this one of these three file extensions. And then from there, after you upload each page, you then hit the submit button to submit your work to the College Board site. Well, the College Board has updated things to, if you decide to still go the route of writing out your work, if you use a particular app, and I know that I personally use, my phone's turned off. I personally use the TurboScan app, which basically I've been using it to post all my solutions to the Google Classroom site. And it's really efficient because I can take all the pictures of all my work all at once and then upload a single PDF file to Classroom. And you can also do the same thing to the College Board platform. And so if you decide to go this route, when you're in the AP demo site, instead of selecting to attach a photo, you'd want to select this option to attach a text file. And again, if you go this route, you would only have to upload one PDF file, and that would make sure perhaps you have all your work there. And then you just hit the submit button once you've uploaded that single PDF file. And this may be an option that you may want to use. I think it might be easier to do it this way if you have the TurboScan app or another scanning app on your phone or whatever device. It may be something that you might want to consider doing to help make it easier for you to submit your work. So the first thing I want to go over today that involves content is revisiting again L'Hopital's rule and limits. So in this question here, we have that selected values of the functions g and g prime and a portion of the graph of f are shown above. So we see that here. The velocity of a particle p moving along the x-axis is given by the differentiable function g of t, where g of t is measured in meters per minute and t is measured in minutes. The functions g and g prime are differentiable for all t greater than or equal to 0. The function f is also continuous for all t greater than or equal to 0. So we want to evaluate this particular limit. Now, when you go to evaluate this particular limit, and if it winds up being an indeterminate form, that is this 0 over 0 or infinity over infinity, if you do this on your exam, I'm guaranteeing to you that you will lose credit. They've said it multiple times, and I've said it as well. You cannot write this here. This is not acceptable. So how can you go about perhaps evaluating things? And I think the best way to try to evaluate a limit on your exam, especially if you see it's a fraction, is to off to the side evaluate the limit of your numerator and the limit of your denominators separately, and then go from there. So that's what I'm going to do. And now to evaluate this limit of this expression here, again, the function f we were told is continuous. So as t approaches 1, we would get, for the numerator, we would get f of 2 times 1, which is f of 2, and then minus 3 times 1, which is 3. And f of 2, if we go to our graph, we see that that value is 3. So indeed, the numerator is 0. So now I'm going to go to our denominator. T is approaching 1. And our denominator has an expression e to the g of t, and then minus f of t. And again, g of t and f of t are continuous, so all this will be continuous. So we get e of g of 1 minus f of 1. But g of 1 in our table here is 0. So we have e to the 0. And f of 1 from our graph, that would have a value of 1. And e to the 0 minus 1, well, e to the 0 is 1. And so 1 minus 1 will give us 0. So we are indeed getting L'Hopital's rule here. And so because of that, because I see this here, now we can start going about applying our L'Hopital's rule. So I will derive the numerator and denominator separately and then go from there. So the derivative of our numerator, we have to be careful. F of 2t is a composition of functions. So the derivative of that would be f prime of 2t, then times the derivative of the inner function of 2t, which would be just 2. And then we'd have the derivative of 3t, which is just 3. And then in the denominator, the derivative of e to the g of t, well, again, it's a composition of functions. The derivative of our function e is still just itself, but then we would need to multiply that by the derivative of the inner function of g of t, and we would denote that by g prime of t. And then we would subtract from that the derivative of our function f, which we would denote by just f prime. And so now from here, we can evaluate our respective, we can just plug in now 1 into our expressions here. So we would have f prime of 2 times 2 minus 3, and then this would be all over e to the g of 1 times g prime of 1 minus f prime of 1. And then from here, right, f prime of 2, we can evaluate that off of our graph. We have our graph of f, and it's differentiable at x equals to 2 here, or just be equal to the slope of the tangent line, which the slope of that line is 2. So we'd have 2 times 2 minus 3 for our numerator. And then in our denominator, g of 1, again, that's just 0, so we can write e to the 0 times g prime of 1, which from our table is just this negative 2. And then minus f prime of 1, and f prime of 1, well, same as f prime of 2, we're on this portion of our graph of f, which has a slope there of 2. And at this point, all of this here is just numerical expressions, which you can input into a calculator. So this here would be our final answer. And the other thing to note is that we're not getting 0 to 0 again for sure. We're getting a non-zero. I think this is 1 in the numerator, and this is definitely not 0 in the denominator. So this would be our final answer. All right, so the next problem here, we're still in the same BC1 problem that I did with the limit question, which is the same information, but now we want to approximate g prime of 5 and then indicate units of measure. Well, to approximate a derivative is just equal to our slope, and to approximate g prime of 5, in our table here, we would perhaps want to find and use the average rate of change on the interval from 4 to 6, right? And so we'd want to approximate the average rate of change on this interval here. So g prime of 5 would be approximately equal to, it would be approximately equal to g of 6 minus g of 4 over 6 minus 4. And then, well, g of 6 we know is equivalent to 8, and g of 4 we know is equivalent to 4. And then we'd have just over 6 minus 4. And this would be our approximation. And then we would have to indicate units of measure, well, for this particular approximation. Well, we were told in the original problem that g of t is measured in this meters per minute, and t is in minutes. So because of that here, this change in the value of our expression of g would be in meters per minute, And then our denominator here, these values of t, is just in minutes. So this here would be an acceptable expression to represent the units of measurement for our calculation, which we don't need to simplify down. But if you want to perhaps say, as I mentioned in a previous video, if you want to say meters per minute, that would be another way to express the units of measurement for this particular derivative expression and what the units of measurement would be for this approximation. All right, the next question I want to go over, it's going to be on the same BC1 problem, so we have the same information. And now I want to go over the average, find the average value of a particular functional expression. And while I had done this prior, I want to emphasize that to find the average value of a functional expression is different than find the average rate of change, which we technically did to help approximate this particular derivative, right? An average rate of change is just a slope calculation, but the average value to a functional expression, you will always want to set up this definite integral expression here when trying to find the average value of any functional expression. And so that's exactly what I'm going to jump right into here to find the average value of g prime of 2 of x over the closed interval, and I'm going to show the work that leads to my answer. So the average value is going to equal 1 over 2 minus 0 times the definite integral from 0 to 2 of g prime of 2x dx. And so now I have everything set up, and now I'm going to show my work to evaluate this particular definite integral. Now, if you know what the antiderivative is for this here, you could perhaps go right into it. Because of this inner function of 2x, however, if you want to, and I'll do it as well, we can do a u substitution to make sure that we find the proper antiderivative for this expression here. And again, the inner function being 2x, that's going to be my u, and the derivative of 2x we know is equal to 2. So that would mean that du would equal to 2 dx, and I don't see any 2 out in front here, so I'm just going to say that 1/2 du is equal to dx. And I'm going to perhaps just simplify what's out in front currently of our definite integral and just write 1/2. And the limits of integration, because I'm setting this equal to this here, I'm going to also, because these limits of integration are in terms of x, I'm going to switch them over in terms of u by using this here. So u is equal to 2x. So when x is equal to 0, that means that u is going to be 2 times 0, which is still going to be 0. And when x is equal to this upper limit of 2, well, then u is just going to be equal to 2 times 2. So the upper limit will switch over to 4. All right. And then inside my integrand, I'll write g prime of u, and then dx is equal to 1/2 du. So I'm going to need another 1/2 here, and I'm going to put that right out in front of my integral. So now we're going to get that this whole kit and caboodle here, 1/2 times 1/2 is just 1/4. The antiderivative of g prime we know is just the function g, and we will need to evaluate that from 0 to 4. And now to evaluate our definite integral, right, we plug in the upper limit of integration first, and then the lower limit of integration in second, and then we can go and evaluate each of these expressions for our function g. And g of 4 we are told is equal to 4, and g of 0 we are also told is equal to 4. And so we don't have to simplify this here, but actually this ends up equaling 0. So for the last problem for today, we're still going to be working on the same BC1 problem so that we have the same information. And what I'd like to go over with you guys is your midpoint Riemann sums. In prior videos, I've gone over left and right and trapezoidal sums. I talked about how to go about doing them. but I want to now take the opportunity now to go over a midpoint Riemann sum. So here we're going to approximate this particular definite integral expression using a midpoint Riemann sum with two subintervals as indicated in the table. So I'm going to start off just getting and writing down this definite integral expression. And now from here, we're going to approximate this. And when you go to do your whatever particular approximation on a definite integral, it's on just the definite integral itself. But because of this 1/6 that is out in front of this definite integral, you should still have that as part of all your work to show the approximation for this whole kit and caboodle expression with your definite integral. But now that I have carried through this 1/6 through to here, now I'm going to go about trying to approximate just my definite integral, again, using a midpoint Riemann sum with the two subintervals from our table. Now, to do a midpoint approximation, what has to occur is that within each interval that you're provided, you want to find the midpoint x value on each interval, and then that midpoint x value, you want to find the functional value there, and you want to use that functional value as part of your midpoint approximation. So first, what I need to do is I need to identify exactly what my intervals are here. So we're going from 0 to 6, so we're pretty much going from here up to 6. And again, I have to have intervals where there must be a midpoint on each interval. So because I see here 1, 2, 3, 4 different intervals to start off with, to get a midpoint or have a midpoint value, if I start at 0, I'm going to skip over 1 and go to 2. And when I go from 0 to 2, I see here a t-value of 1 is directly in the middle of those two. And now I'm going to use this functional value here for my first interval and my midpoint approximation. But then my second interval, and this is where students get tripped up, my second interval, you always start off where you left off from your prior interval to get the next interval when doing a midpoint approximation. So my next interval is going to start here at t equals to 2, and then I'm going to skip over 4 and go to 6. And from 2 to 6, that's going to be my second interval, where 4 is directly in the middle between 2 and 6. So now that I see clearly what my two intervals are, I'm going to now do my midpoint approximation. And again, I'm going to get my g of my value for my function of g on each interval and multiply that by my delta t on each interval, because that's what I have here that I'm trying to approximate this integral with. So again, the first interval, my midpoint t value there is 1, and g of 1 we see is 0. So that's my functional value for g and the midpoint value in that first interval. And our delta t here is 2. And then on the second interval from 2 to 6, our midpoint t value there is 4. And it just so happens to be that g of 4 is 4. That's our functional value at the midpoint of that interval. And then the delta t here is 4. Right? And then all this here would be your approximation to this definite integral expression. So I hope that this video helped clarify and explain certain things that you perhaps have been seeing during your review. I'll post some more questions today that just have to do with just more practice. And if you have any questions on any of those problems or anything in this video, as always, please let me know. And as always, please take care, stay safe, and I'll talk to you soon.